Recording.
Okay, Pete, over to you.
Thank you. Hello and welcome to our webinar. I'm Pete Starkey, a member of the Council of the Institute of Circuit Technology, which is dedicated to technical aspects of printed circuit board manufacture and assembly. The Institute continues to successfully provide its members with opportunities to improve their knowledge of manufacturing process technologies, materials and practices, and to stay in touch with current and future developments. The future of printed circuit manufacturing and assembly will rely heavily on automation and the establishment of the smart factory. What will this involve, and what additional skills will engineers need to learn? A leading expert in this area is Happy Holden, Honorary Fellow of the Institute of Circuit Technology, who has kindly offered to deliver a series of 8 one-hour webinars based on his recently published ebook, 24 Essential Skills for Engineers, which is free to download from the iConnect 007 website, and which will form a valuable resource for in-house training of engineers and their career development. For the most effective results, Happy has advocated selecting your own engineers who are already familiar with your own processes and procedures and letting them learn how to do the automation planning. Then they can teach others this essential skill which the factory will need over and over again. Happy began the series with an introduction to the elements of automation and the journey to your smart factory, and discussed the key issues: who, what, how long, when, and how much. He has already discussed a series of skills, including total quality control, Six Sigma and statistical tools, problem solving, design of experiments, predictive analysis, benchmarking, product and process life cycles, engineering economics, and road mapping. He has defined automation and automation methodology, and last week examined the realities of the smart factory. If you missed these earlier sessions, they have all been recorded and will be made available to you. In today's presentation, the 6th in the series, Happy discusses sensors and chemical analysis. If you have any specific questions, please direct them to happy@iconnect007.com. So Happy, over to you.
Thank you, Pete. Let me get started here. So this is the 6th in our series, and personally, one of my favorite. We're talking here about sensors and chemical analysis for printed circuit fabrication and assembly. And that's because although there's lots and lots of sensors out there in the market, they're mainly designed and installed in larger chemical plants with larger staff and things like that. For the printed circuit fabrication and assembly, that's harder to come by. So, like I said, this is the 6th in the series that we'll be doing out of the 8, the sensors and chemical analysis. This comes from chapter 4 of the other free ebook we've asked you to download. And the chapter 4 is more detailed than the 60 minutes I'm spending here today. Before you think of some questions, download and read through chapter 4, see if that answers your questions before. Otherwise, if not, send it on to me. I've added several new slides, which I'll update Bill on, but it's going to be recorded today. Chemical reaction rates, especially in printed circuit fabrication, are highly dependent on concentrations of ingredients, such as here the deposition of electroless copper, in terms of grams as a function of copper concentration and time, or etching 1 ounce copper in terms of copper etching concentration of grams per liter. All of these parameters are important. And as we emphasized last week, the really essential element of the smart factory is the increased collection of data from sensors and utilizing that data to make predictions and understanding of your manufacturing process to improve productivity, improve quality, yield, or any other particular business objective. When you get into electroplating, which has always been my focus as a chemical engineer, there are a lot of parameters that influence plating and techniques like that. So today we'll talk more about sensors and areas like that I spent a lot of time working on and developing. The impact of these various plating parameters you can see in terms of relatively influence. The interesting thing there on terms of most influential, contact resistance is one that a lot of times maintenance and everyone doesn't pay attention to, but resistance can build up on your plating racks, things like that, and have enormous influence. So preventive and predictive maintenance that we talked about is a really important one. But the last one, pattern design, is not one that you control. That's the artwork you're getting from your customers. And so that is one of the most important, and somehow a DFM program to help customers understand do's and don'ts of printed circuit design that'll affect plating parameters is really, really important. Like I say, the digitization or the smart factory is basically one of sensing, connecting these sensors and data, and then predicting them to have an outcome improvement that you haven't had before. But the sensing is not just the sensing of data and activity, but it could also be interfacing to the automated machines that you purchased that's running things, that is running their own loops, but you don't have access to some of the information they have. And so tying into smart equipment, again, is part of the programs we're talking about today. Some of you, may still be doing manual analysis, thing called the Hull cell. You see right here, been done for the last 50 years. It's polished brass panels placed at an angle, and then a sample solution put in, hooked up to the power supply, and then plated, as you can see here, acid tin, 3 amps for 5 minutes, or acid copper, 5 amps, 5 minutes, or a deep gold. Hewlett Packard is famous for our copper tin nickel gold process. The tin nickel is not tin and nickel. It's a unique alloy that's tin and nickel in a chloride bath, non-proprietary. We were only one of two in the entire world that used that. But if you look up the history, you'll find that tin nickel is far superior to nickel as a barrier plate. And over that, we would put our gold flash. So 1/10 of a micron of gold flash over tin nickel outperformed in Bell Lab studies 100 microinches of gold over sulfamate nickel. Interesting that they didn't want to publish that, because their 100 microinches being outperformed by Hewlett Packard's 1/10 of a micron process was kind of embarrassing for them, even though they switched to our process later in life. There's a lot of wet chemistry and manual titration. Part of this thing is if you're focused on automating a lot of the chemical laboratory and manual work, and we'll talk about that the rest of the day. The common sensors usable in a printed circuit or assembly are listed here. There's probably far more, but one's things like mass flow meters, specific gravity, a temperature, pH probes, flow meters, inductance, time is an important one, ampere hours, weight, pressure grade, level. These are all common sensors that potentially could improve and be part of your program. One of the most important are these non-contact sensors that can read lot code. And these are some of the different ones you see here. Either the DMC code that may be on a carrier, or it could be a drill code that you put in after drilling, or a barcode that you put in as part of the imaging or part of the solder mask and legend type. But anyway, we talked about the Wheeland facility that has nearly 120 of these readers to automatically direct the process flow because of all the different types of customers, different types of copper thicknesses, different materials, and different products that they build interchangeably within their system. Hopefully people will write talks about their etching system that can simultaneously handle 5-micron copper and up to 6-ounce copper on inner layer, outer layer etching in the same machine at the same time. And that's improvement in productivity and quality. If you're, you can always ask the question, how is that possible? Well, it is possible, being done 24/7 with the ability to move down to under 5-micron lines and spaces. My favorite sensors are what we call the electrochemical sensors. That is capacitance, conductivity, pH or ion selective, oxidation reduction potential, or cyclic photometer stripping, CVS. So here's a kind of a rundown of their sensitivity, whether or not it can be used in non-conducting fluids, maintenance, installation, and cost. What these you see here is, conductivity in millimoles per centimeter, measuring sulfuric acid conductivity or sodium chloride conductivity as a function of percent concentration, or pH for either base reagents or acid reagents. Ion selected electrodes are used throughout the world, and you can see from the list here that they cover a lot of elements that are used and are part of printed circuit or assembly and other cleaning processes with their range and techniques like that. My favorite one that is not used as much as it should be is specific gravity. You all have probably worked with the hydrometer, which is inexpensive, easy to use glass hydrometer. You can buy these different ranges and essentially drop them into any tank and read out the specific gravity. Another one, the displacer, is typically used in etchant control. Hydrostatic head is one that, rather than a set point, can read out continuously. There's radiation and a weight of fixed volumes and the vibrating U-tube. Specific gravity works really well because we're dealing mainly with aqueous processes, and our etchants, our cleaners, even our electroplating are aqueous processes. And because of that, anytime you dissolve something in there, you're going to change the weight concentration, grams per liter, as a specific gravity, or degrees Baumé as an older blend. Shown here is sulfuric acid, copper sulfate plus sulfuric acid, hydrochloric acid, in terms of its specific gravity being related to weight concentrations in grams per liter. It's easy to do. Like I said, you just buy these hydrometers inexpensively, drop them into a sample. Any operator can do this. And in fact, this should be part of your specific process control, is have operators routinely, measuring critical parameters and writing down in the log. Now, as we talked about, that's not automated at all, but if it proved very useful, then consider that as installing an automated specific gravity. And we have one here that I've designed and used for the last years, which is it's extremely sensitive specific gravity, more sensitive in terms of its adjustment than anything you can buy today. This one is based on a GEMS level switch where we removed the cap and we machined this CPVC bolt there, which we threaded. We have two CPVC nuts that go on threaded end, and then the drill depth, you drill it out. And this right then is then epoxied onto the end of the reed switch, and this becomes one of the world's most sensitive and useful specific gravity sensors anywhere. Here's the calibration, and just pick your specific gravity operating point and pick your specific gravity span that you want. And this will then give you the drill depth and the nut diameter to go with that. This is part of a basic program I wrote back in the late 70s. So if you change anything, then you'll have to rewrite and change parts of the program. This is a test for you chemical and mechanical engineers out there to explain how this displacement specifically works, because it's based on the principle of the center of gravity as opposed to the center of buoyancy. And that's be interesting because the chemical engineers may be a little more cognitive of this than the mechanical engineers. I remember the fight we had because the mechanical engineers said this will never work, and yet it did work until we finally explained to the mechanical engineers that the center of buoyancy when you're fully immersed is the center of displaced mass. So no matter where you put the nut, what's being displaced doesn't change, but where you change, when you screw that nut in and out, you change the center of gravity. And so these opposing forces, the only thing that will make that thing close the switch is a change in the specific gravity of this displaced mass. If you want this to be a continuous readout of any specific gravity, then instead of having a fulcrum at the end, you put the fulcrum in the middle, seal the drilled out portion, and then buy a tilt sensor to do that. And depending on, as this device tilts, it will read out directly in the specific gravity. I'll let you do the rest of the work on that. Other ones available that we've built are differential pressure meters. As far as I know, you can't buy one of these, but this works very well if you want to go through the mathematics. One that works very well industrially is this titanium metal chain and a constant volume displacer and LVDT coils that then read out how high or low this thing floats, but it's expensive. Examples of how specific gravity helps long run is this control of peroxide sulfuric etchants as a function of measuring the temperature of the thing in red and the specific gravity of that, and then using this calibration chart to figure out the copper sulfate and sulfuric acid levels without having to go to a titration and a chemical lab. So this can also be easily automated, as we talked about, with and hooked into a simple data acquisition system. Another very, very useful, if you don't have it right now, is ampere hour meters. The ampere hour is simply measured by putting a 50 millivolt shunt into the DC supply. You can put these on every cathode bar, or you can put them for the entire tank. What you see here is ones that I built. These cost about 80 cents to $1 US dollars to make and use an op amp as a voltage to frequency, and then a counter that electronic or mechanical that provides for addition of chemicals based on the ampere hours. The ampere hours correlates very well with concentration of chemicals, and so this, provides a continuous improvement rather than large swings. Ones that I like to start people out on is the techniques that we use to control the chlorine level of home pools. And that's typically done by taking a sample of the pool water, putting a couple of drops of reagent into a bottle, shake it up, and then compare it with a color chart. Hopefully you're not colorblind on this. More sophisticated ones have a round wheel that you hold the two up, and you can turn it until you match the color perfectly, and it gives you concentrations of that. Well, these have been developed for almost every type of electroplating and many other processes have you shown here. And these different test strips or devices are inexpensive and easy to use, and to train operators to do that. Some of them have been automated in terms of having to interpret that color-wise. You should stick it into a reflection meter such as this that's sold, or you can use different types of spectrophotometers that you've seen here. Some of these spectrophotometers, like these Spectronics 20, go back to when I was in high school, but are still working and usable today. There are battery-powered ones, portable ones, et cetera, et cetera. These are some of the newer ones that you might see that are automated with LCD readouts and graphs. I want to kind of introduce one that Hewlett-Packard actually developed called the diode array spectrophotometer. And the diode array is different in that we use a stationary holographic grating. And by having the grating, we actually disperse the incoming visible sample and use a diode array, semiconductor diode array, to actually scan for the amount of light, thereby taking a millisecond. And so instead of being a number of minutes for analysis, the analysis are done in milliseconds. These things started with the HP 8450 back in 1980 at $13,000. And then the 8452 was $8,000, you see here in the bottom. And the last one from Agilent, the 8453E, is $4,200. This is a machine that I recommend that you consider if chemical analysis or chemical sensors are part of your improvement program, because these spectrophotometers, taking the samples will automatically create an equation based on concentration and give it back to you as part of their computer software built into the machine. And so one of these in the laboratory will really help you. And then you implement it with a do-it-yourself spectrophotometer, such as seen here. You can build these things very simply. And one of the reasons why I say that is that if you go to this URL, you'll learn about the junior high and high schools around the world using the Lego spectrophotometer that they built themselves, that you see there in the upper right. And there are different experiments, how you build this, use it. You don't have to use expensive gratings. You see right there, any old CD can be cut up and used as a grating, because That's one reason why it's prismatic when you look at it. It diffracts light much as a ruled grating would do. But you can buy a ruled grating for this. Anyway, once you figure out wavelengths of specifics, what you're interested in, the processor you use, instead of being part of the laboratory, you can delegate it down to being continuously monitored by one of these Lego spectrometers you build yourself. So in order to emphasize that, we had done a lot of work in replacing our titrations and atomic absorption measurements with the diode array spectrometer. And so here are comparisons of atomic absorption or titration versus colorimetric tin plating, alkaline etchants, acid copper plating, micro etches, copper chloride etches, palladium catalyst. And you can find this in the Metal Finishing Magazine, March of 1985, when we published all of this data. Here's some of the wavelengths of our different nickel plating baths used. And you can see that 80 grams per liter, 85 grams per liter, and 90 grams per liter at these particular absorption at particular wavelengths from the UV visible diode array. The same is true for the organic additives on the nickel bath, a new nickel bath component, the saccharin, and the background for the nickel bath. The same is true for curves for palladium and a catalyst and or gold in your operation, or it could be that of the wash water and a final assembly, et cetera, et cetera. A more complicated machine is a voltammetric or CVS that you can see right here, a couple of different ones that analyze electroplating baths. And this is cyclic voltammetric stripping, CVS, developed by Tinch and Ogden in the 70s while I was still a process engineer. Knew those gentlemen well down in Los Angeles. One of the things that I did is that my focus was to get a CVS on every single one of our plating baths, but at $20,000 or so for a laboratory, that's not practical. But fortunately, living in Asia, Asian universities have developed low-cost CVS for diabetes detection. And what you see right there is a $200 CVS copied from the universities that published the schematics and how to build these things. Again, they're using it for diabetes detection, and essentially we're using it for additives to copper plating or other types of plating. Interesting enough, the organic and aqueous additives that they're detecting for diabetes is the same chemical compounds we're interested in terms of brighteners and levelers. So that's one reason why it works so well. It's just that, again, no one sells these $200 units, but you could go back and track them, and it may be something that you want to build yourself, especially because you can make the printed circuit boards and assemble them yourself. There are other things, paramagnetic and coulometric probes that are out there, magnetic probes, induction probes, eddy current probes, coulometric probes that are available also as laboratory that can be automated, put into it, as well as X-ray fluorescent and beta backscatter for measuring your various coatings and thicknesses. The big thing about going to more frequent analysis or concentration through a controller is that right now, as you use production, without online controllers, your concentration is very up and down. And sometimes they dip below the minimum. That creates problems. But if you don't capture it right at that spot, you can't figure out why, you have 1 or 2% of, yield problems but nothing catastrophic or large. Once you put a controller down there, and a controller is much easier to build and run than is an analyzer. An auto analyzer runs from 0 up to some concentration levels and has to follow Beer's law. Whereas a controller at a set point only is looking for a deviation from that set point. So controller is much easier and cheaper to build than is an analyzer that you might have in the analytical lab. But as you reduce your consumption range, you also reduce your costs and improve quality. So without controller and with controller. So higher yields and lower costs is an advantage. And other types, you may employ, instead of manual titration, automatic chemical titrators, such as seen here. So these kind of things are put together in a typical automatic chemical solution controller. He is typically built with a specific gravity sensor, 1, a colorimetric metal concentration sensor, 2, a pH or an ORP sensor is 3, and then may have a CBS sensor is 4. All these put into a controller and recorder that you can set up. The most standard one for me goes back to the 1970s when I built my first one for electroless copper controller. You can see here, analyzes the copper colorimetrically, and electroless copper analyzes the OH radical using a pH after hydrochloric acid is added, and then analyzes the formaldehyde again after sodium sulfite is added. And then if you look in the book, you'll see pictures of these homemade electroless copper controllers. But fortunately, I was following on the work of photo circuits that had fully additive electroless copper, making additive circuits. And photo circuits did the original work a lot on this. But I spent a lot of time working on improving copper plating, especially for hole filling and blind via filling. This is my my research tank on the left there. This is the cold one. There's another version that heated, built, more robust material. But, with that, we would take a sample and look at specific gravity, specific ions, pH or ORP, organics, colorimetric, and conductivity as part of optimization and basic research, especially in the use of inductors and insoluble anodes, our work. You can buy these. Aditech is very famous at producing and selling these available. You can see here automatic controls for electroless coppers, CBS, copper plating, available from Aditech that you've probably seen in the short video of Whelan and the green source, where these handle 100% of all the chemical dosing and analysis. This is a Japanese automatic titrator controller that's available if you look through the internet at ones that you can buy off the shelf. Other ones that are sold by different companies, things like developers and strippers, which can be controlled by a simple pH shown here, or simply counting the number of panels and area process using those sensors I talked about in very few slides. How much square centimeters of work is actually going through this stripper and developer, and using that then to control the replenishment of strippers or developers. These are micro etch controllers. One on the left is a colorimetric, using some of the examples shown you earlier. The one on the right is a hydrometer displacer. Not very accurate, unfortunately, but still that's a lot of people that put these together didn't understand exactly how a hydrometer works in terms of its mathematics and volume and displacement. The one I showed you is optimized for printed circuit fabrication and etching. A lot of the other ones are just blocks of metal or glass that they buy, not specific. Micro etch controllers and photoresist stripper controllers, some other ones available, pretty much, especially for copper chloride etching. Very common to have one of these available. If you're integrated circuit fabrication, then you have bath controllers. They're a lot more expensive. And here you can see is one for the copper pillar plating used on semiconductors, the wafer fab. These are top of the line units. And you can see that they have the chemistry as well as the reagents. And then looking at chloride, brightener, leveler, all the different organic and other additives specific to keep this very tightly controlled within the range they want. One of the ones that we implemented because of our nickel and tin nickel plating, we had 3 2,800 liter of these baths doing all of our barrier between our finish and our copper plating, and using the 8453 diode ray, things like that. We would needed only 2 reagents, hydrochloric acid and sodium hypophosphite, which were then run through peristaltic pumps, mixed together, and then would control the nitrogen of the nickel sulfate additive and the PC3 leveler brightener additive to the nickel plating baths all online. And then just once a week, the laboratory would monitor the readouts and anything needed calibrating. So these are, there are various data acquisition systems we've talked about. Like I said, this 4-channel analog one is $85. This 8-channel analog one with Ethernet, $800. So you can find anything between $50 and $3,000 available as data acquisition systems to tie various sensors that you want to try out with together. And then for a computer, I prefer the Raspberry Pi 4 you see there in the middle. That's $42. I prefer that because it comes complete with wireless Wi-Fi, Ethernet, and 2 different high resolution readout monitors, as well as if you go to this MCC company, they produce data acquisition hats that for $99 just plug into the pins on your Raspberry Pi. And so now you have a complete data acquisition system, as many channels as you want. Or you could have the Arduino, which is $40, or the industrial Arduino, the Portenta, which is $72 to $105, or a simplified Raspberry Pi for compute, which is only $30. So these various microcomputers are available on the market to control Earth. And like I talked about last week, the Seika Corporation, India, has one for assembly and integrating assembly and sensor and facility sensors back into it. So this can be interfaced and provided to IPC CFX, either by radio or power line, what they call the shoebox monitor. And so you can look at that, but I'm advocating that you can buy your data acquisition system, buy your Raspberry Pi. And so I propose that you should consider maybe in one of your do-it-yourself process control projects, designing and building the specific gravity sensor, interfacing that to one of the data acquisition ones, interfacing that to a Raspberry Pi, and then write your program in Python. And Python is the preferred language using a Raspberry Pi because it's a Linux operating system, if you're not familiar with that. And what you have then is a complete controller or diagnostic unit that can also talk to higher level software that you might have in your management information systems and things like that. You've got to start somewhere. We'll start with maybe one of the easiest to solve or one of the biggest opportunities. Because if you can move on using sensors, then these advanced sensors are like this inline 3D confocal sensors. This is the latest of the integrated circuit ones, in which these things can be built over a conveyor, and they can be set up to measure individual line width very, very accurately, individual spacing, and so that you can have a continuous readout from a conveyor of all the work going through your factory, provided they only sell the sensors. They don't sell AOI systems. And this is not an AOI system, but it's significantly cheaper than an AOI and very fast. You can achieve submicron resolution with that to easily integrate into a custom inspection system. But it's probably not the first project. This is one, once you've got the whole thing of Python programming, interfacing, working with maintenance or someone that can build the mechanics to support this, you can actually have an inline inspection system provide continuous readout with that. And lastly, if you want to start to master process control, then you can start to look at, what kind of control elements do I want to employ? Not just proportional on and off, but do I want integral and derivative control elements like that? But it's all going to depend on deployment prioritization. You should look at, of all the projects working with that are being proposed, what are the greatest business impact in terms of payback? And at the same time, what is the ease of implementation? And in the upper right-hand corner, what we call the low-hanging fruit. There should be priority one. Those should be the first projects because they're the easiest to implement, but have the greatest business payback. After you've cleared out all the priority one, then the priority two improvements that are easy to implement, but not as great as business impact, and then move on to the upper left hand. They have a large impact, but they're harder to deploy, like that confocal system, and proceed with caution in the lower left, which have lower business impact and are much more difficult to implement in terms of that. Because you want to start small, grow, and learn. And so this is kind of the citizens development model. That is, rather than a product line, this is what your technician, your engineers, your workers put together in terms of being a citizens developed model and looking for low risk pilot projects using case by use case as a pilot. And then, as you gain on that, moving up in terms of value and implementation, involving more and more people once they're trained to move along with this. Because this predictive analytic journey, you really need to prove of value. So it's, it starts with the factory assessment in terms of benchmarking and putting together roadmap, prioritizing, education and technical workshops to look for examples, and workplace strategies, and doing the business case ROIs, assessing gap analysis between you and competitors, or you and what your customers want or will need in the future, organizing, and we talked about then proof of the value in terms of technical deployment, training, and achieving the ROI, and then scaling lessons learned and training others in terms of delivering that. So the evolution of this starts with it. Now, you know, in terms of other ebooks that I talked about, here's one, Fundamentals of Sensor Measurement from Keysight Technology, that's free, that you can download. That's useful for that. Another one is from Tektronix, in further reading, you know, Low-Level Measurement Handbook, and it's a free ebook from Tektronix. And it's good information for electrochemical sensors and, you know, like that. So thank you for your time today. The actual ebooks have more information available. Unfortunately, there's not a lot of case studies. We would love to publish and make available case studies if any of you are so inclined. You know, the problem is that once we're successful, we like to, you know, keep that as proprietary. But we're all in kind of the same boat and need to, what you may learn from someone else, if you provide some of your examples and they learn from you, we can best solve these problems in the future by working together rather than individually, and or utilizing students in summer jobs or university program, etc., as part of working together with this. Calumet been very successful with delegating some of the tougher engineering ones to the university, that they're at Michigan Tech University, and then employing some of the key students full-time in the summer, allow them to continue to work, especially if they're involved in a senior project that they've got to write up. Many times these printed circuit or assembly problems being solved are ideal for senior projects, for that to go on to lead to more work in graduate school, etc. With that, we thank you for your time, and hope to see you back here same time, same station next week. With anything else we can do for you, be sure to contact us or Bill.